So like I said, this is really sort of like a 1 week topic, and I want to begin by just recapping what we saw last time. So what we're seeing now is the idea that we don't just say, well, you can interpret an integral as an area, which is one thing that you can do, but rather what we're going to start doing now is we're going to use integrals in order to solve other problems. So what we want to talk about right now, or what we're doing right now, is saying we're going to be able to find the volume of a solid object using an integral. And how do we do that? So the basic way to do it is what we talked about last time, which is to say that in the same way that the integral of a function dx gives you the area, the integral of an area dx gives you the volume. So that was the first straightforward way that we thought about this. So one of the things we said is, so the first thing we said is if we have a base and then we know what the area of each cross section is, we can mentally set it up in the following way. We can say each cross section has a width delta x, which we will eventually make dx, and then it has a certain area. So here's a picture of an equilateral triangle. We know the formula for the area of an equilateral triangle. Or we can make them squares. Obviously, we know the formula for the area of a square. And then all that's required is you have to know what that side length is. But then that side length is determined by, I don't know, some formula or something. Okay. So to do something like that, so here's an example where we're looking at a square. We figure out that the side of the square is 2 minus x, so the area of the square is going to be 2 minus x squared. That's the area, so you just integrate that. And that'll give you the volume. Okay. And we can do this saying that our shape runs along changing x values, in which case we're going to integrate, and each area is a function of an x value, so we're going to integrate along dx. Or the shape runs along y values, and the area changes as a function of y, and then we're going to integrate dy. Or it's a function of r, we integrate dr, whatever you like. Okay. So known cross-section, that's the first basic one. Second one, solid of revolution. Here the idea is that if you have a function and you twirl it around, say, the x-axis, we know what kind of cross-sections it'll make. So here's a function, and there you go. Again, we imagine these thin slices, and again, notice that these thin slices are running as x changes. So our variable is x, so we're going to wind up, these are delta x, and we're going to wind up integrating dx. And when you twirl this around the x-axis, what you wind up with are, you could think of them as very flat cylinders, but they're typically referred to as disks. And so obviously in that case, when you take a cross section, you get a circle, and we know the area of a circle. It's pi r squared. And we need to figure out what is the formula for r for a given x value. Let's see. Now there was a variation of this that we saw, which is what if you're revolving not around the x-axis, but what if you're revolving somewhere else? So once again, you need to, so for example, in this problem, once again, you need to figure out, okay, what is my radius? So it's a circle, so it's going to be pi r squared. What's r? So in this case, your function is y equals x squared plus x plus 2, but you're revolving around the line y equals 1. So your radius isn't just the function, it's the distance between those two spots, which is the function minus 1. And the graph helps, I think, helps you confirm that. Okay. Now, disk with hole. So this happens when you have two functions, and then you revolve around yet another line that's separately defined. So here is one example that we looked at. So suppose you have the region enclosed by y equals x and y equals x squared, and you rotate it around the x-axis. What do you get? Well, once again, there's the region. So when you rotate it, there's going to be stuff missing. And that's the hole in the middle. So if that happens, how do you find the volume of the resulting solid? It's quite easy to do. Check it out. You simply think of it as the outer function revolved, and that makes a solid. And then there's an inner function that also revolves and makes a solid, but that's the solid that you're removing or taking away. So you think of it as the outer volume minus the inner volume. So I think that makes sense. So if you set it up, so this is easy to set up as two separate integrals. So I have volume, I switched between F and G. Okay. So the volume is volume 1 minus volume 2. Volume 2 naturally is the one that you're taking away. And so that's just the integral of a1 dx minus the integral of a2 dx. The first volume, the outer volume minus the inner volume. And each volume is pi r squared. So you get the integral of pi r1 squared minus pi r2 squared. And notice in particular, you cannot do r1 minus r2 and then square that. That is a totally separate thing. You have to do one volume minus the other volume. And then we have to use the technique that we learned from finding enclosed area, where you have to figure out where the solid starts and stops in terms of x value. So you just set the two functions equal to each other, and that gives you the endpoints for your integral. Okay. So let's continue. Let's do another example of this disk with hole. Okay. So take this region enclosed by y equals x and y equals x squared. Oh, that sounds familiar. And we're going to rotate it around y equals 2. And what is the volume? So once again, strongly encourage you to draw a quick sketch. Exactly. So, and again, these are simple functions, and a rough sketch will give you enough that you need. I had someone, I think I saw someone's work, and they had very meticulously drawn exactly what the function looked like, plotting points and all that. You don't need that. All you need is a rough sketch to show you approximately what you're dealing with. So for example, y equals x, I know that gives me a line like this, and y equals x squared, I know it gives me a parabola. So this, like this. So just doing a rough sketch, I can quickly see that there's my sliver, there's my region, and as always, we find the endpoints. So x equals x squared, 0 equals x squared minus x. So you factor out an x, and you see that x equals 0 and 1. So that gives you your endpoints. Now, something interesting happens here because we're not rotating it around an axis. So let's make a little more room. Okay. So where are we rotating around? Well, we know here is y equals 0. Over here is y equals 1. But where we're rotating around is y equals 2. So it's going like this. Okay. So let me ask you this. Which function now determines the outside volume, and which function determines the inside one, which is the whole?
Outside is squared inside.
The outside is now x squared. Okay. So actually, let's just do this. Okay. So we know we're going to get pi r1 squared minus pi r2 squared. And the question, actually, I very quickly wrote down dx, but we should confirm that we're actually going to be using dx. So why are we using dx? Well, we're rotating it around the line y equals 2. So we imagine a thin slice like that. Rotating it around will give there you go. A little sloppy, but you get the idea. Rotating it around like that will give you a disk with a hole punched in the middle. And again, we've cut a slice that uses delta x or dx. Okay. So what is the radius of the outside circle, the outside solid? Okay. So what we need is to figure out where's the radius on this picture. So the radius, obviously, one end is going to be the center where it's rotating, and the other end is going to be the function itself. So that is R1. And the question is, what's that distance? Yeah. So you could think of it either as x squared minus 2 or 2 minus x squared. Turns out that it's a radius and we're going to square it, so it doesn't matter. However, to always be safe and consistent, you should always take the bigger one minus the smaller one. It just so happens that here we're going to square it, so it won't actually matter.
If it was moving down, it would be plus 2, right?
I'm sorry?
If it was minus 2, it would be plus 2.
If it was, you mean if it was down here? Yeah, if it was down there, you would subtract negative 2, so it would be plus 2. Okay. So R1 equals 2 minus x squared. And then what about R2? What about that inside radius? 2 minus x. Because it, now my diagram's getting messy. So going from the axis to the graph, that right there is R2. And so that distance is 2 minus x. So 2 minus x squared minus 2 minus x squared, all dx. Okay. All right. So as you're getting used to doing these problems, definitely a picture is going to help, especially a good picture and a neat picture. eventually when you get used to it, what you'll see is, oh, here's my function is y equals x squared. The axis is y equals 2. So my radius is just, well, x squared minus 2, or more properly, 2 minus x squared. So algebraically, it's just like that. But you may want to continue to draw a picture just to help support you as you put that together. Okay. So anyway, so now we have our integral, and we simply have to do it. So how do we do this integral?
Factor out the pi.
Okay.
Factor
So
out the pi,
one
open up.
one useful thing to do is to factor out the pi.
And then also open the
Right.
yeah, distributed.
Right. So you've got 2 minus x, everything squared. If we just multiply that out, we'll just have a simple polynomial. And that's easy to integrate. And the same thing with the 2 minus x squared squared. So you'll notice that in these problems, you're always going to have a pi r squared. So a lot of times, you're just going to want to multiply, whatever the r expression is, it's squared. A lot of times, you're just going to want to multiply it out. So that's going to be very common happening here. Okay. So this becomes 4 minus 4x squared plus x to the 4th. And then this one is going to be minus, and we have to be so careful about this. So I'm just going to put it in parentheses. 4 minus 4x plus x squared, all dx. Okay. So why do we have to be careful? What's happening there? Signs. Oh, exactly. You guys know it. All right. So notice that it's so tricky. I did not want to A, multiply that out, and B, do the signs in one step in my head. Because when you do that, what's going to happen? You're going to make a mistake. I got some money in my pocket. I'll make a wager. Okay. So minus 4 plus 4x minus x squared. Now what?
Cancel out.
Yeah.
4, cancel out 4.
Again, we're still doing algebra. We're doing algebra to help us out. So this is now, okay, plus 4 minus 4, great. So I've got x to the 4th. Then I've got minus 5x squared and a plus 4x. And that's how that simplifies. And obviously doing this integral now is completely easy. All right. So the hard part is everything other than the calculus. Okay. So this is now x to the 5th over 5 minus 5x to the 3rd over 3 plus 4x squared over 2, which of course is just 2x squared. And that's all going from 0 to 1. Okay. So you plug in 1, you get 1/5 minus 5/3 plus 2. And when you plug in 0, what do you get? It's true you get 0, but you should always check that. And just a comment here, I've seen people assume that plugging in 0 will give 0. Not the case. So check it. And so all of that winds up being okay. If I did that correctly in my head, that's what you get. Nope.
Should be 8 over 15.
Yeah, it should be something else, shouldn't it? Okay. Yeah, 8 over 15. Thank you. Okay. So what's the hardest part about doing this problem and ones like it? The algebra is one of the hardest parts. What else?
Setting it up.
Setting it up. I would say like step 1 is the hardest part. Okay.
I have a weird variation.
Okay. So this is the setup of how to do that. Next. So now we've got a region bounded by x equals 0, y equals 1, and x equals y to the half, which is the square root of y, and we're revolving around the y-axis. So what does this look like? So what does the graph look like, roughly? Can we figure this out? So it looks approximately
Oh, the other way around.
like this. Now, how did I know that? Yeah. So x equals the square root of y. If you think about that, what is that as a function of y? Excuse me, what is that if y is a function of x? Y equals x squared. Okay. So you didn't have to do that necessarily here, but we're going to see problems where thinking about that is going to be helpful. Anyway, that's a side note. Okay. So we've got this. We've got x equals 0. And we've got y equals 1. Okay. And it's revolved around the y-axis. Okay. So how are we going to revolve this around the y-axis? Yeah. How are we going to take a slice? Well, if we use dx, what would a slice look like? Dx would look like this, and we're going to revolve it around that way. Okay. That gives us something else that we're not familiar with. We're going to see it later.
We could do it, but it's really hard.
Right. But right now, we're going to stick to trying to make discs. So how would you make a slice that gives you a disc?
Horizontal.
Cut a horizontal slice, exactly. So if you cut a slice like that and then rotate it, you get a disc. There you go. Okay. Now, in this case, the small slice that we made, is it dx? It's dy. And you can see because you're cutting little slices going vertically. So, first of all, this horizontal slice means you're going to have a dy. That's the first important thing. Second thing, so we still know that we still know that the volume is going to be the integral of the area, but now we know that area is going to be a function of y, and we're going to integrate dy. Okay. So next, what is the well, still it's a comes from a rotation or a revolution. So what is the shape? It's still a circle. The area is still going to be pi r squared. So pi r squared dy. Okay. So now we have to ask ourselves, what's the radius? Sorry? Exactly. The radius is the x value. And what is the x value? Y to the half. And there's one thing that's missing from this integral to make the setup complete. The boundaries. So we're integrating starting at what value, going to what value? Okay. 0 to 1. Now, are those x values or are those y values?
Y value.
Those are y values because y is your variable you're integrating dy. So you have to say that y is going from 0 to 1.
So that,
There you go. Okay. So that's the setup. Oh. Okay. So now how do we do this integral? Yeah. So now it's just the integral of pi y dy. Now we can do that integral. You get pi y squared over 2 from 0 to 1. That gives you pi 1 squared over 2 minus pi 0 squared over 2. And that just gives you pi over 2. So the boundaries in this case were moderately evident, but you're right. Sometimes you're going to need to actually figure it out. So how do you figure out boundaries? Well, it says, let's see. So it says bounded by. It says the region bounded by y equals 1. So that gives you one boundary. And then it says so the other boundary happens at x equals 0. Well, then it's just a question of when does x equal 0 intersect with our function. So when x equals 0, what's y? Y has to be 0. So this one gives you the upper bound. So this one gives the upper boundary, and then setting 0. In this case, you would get 0 equals the square root of y, and that gives you y equals 0, and that's your other boundary. So that being said, you can do it algebraically, but I really think it totally helps to draw the graph. So that gives you a better sense of what you're looking for. Okay. And of course, when I say draw the graph, again, I just mean a quick sketch. Okay. Okay. Next. So the region bounded by y equals ln x, y equals 1, y equals 2, x equals 0, and that's revolved around the y-axis. So what do you do?
Quick sketch.
Quick sketch.
See the boundary.
Okay. So what does this look like? Yeah. So ln of x looks something like that. And then what else do we have? Well, we got x equals 0, which is the y-axis. Then we got y equals 1 and y equals 2. So there's our region in there, and we're going to revolve around the y-axis. So which way do you think would be nice to make slices? Horizontal slices. Okay. And would you say that we're going to do this dx or dy? We're going to go dy. Okay. And having said that, what is, let's see. So how are we going to set up the integral to find the volume? What's the shape of a cross-section? It's a circle, so it's going to be pi r squared. And the question is, what's the radius?
In y, okay, so just rewrite.
Right. So just like before, the radius is simply the x value. So does everyone see that? The radius is a horizontal distance. So that's measured by x. So the question is, what's x?
E to the y.
Well, we know that y, so hold on. So radius equals x, and the question is, what's x? Well, we know that y equals ln of x. So then what does x equal? algebra.
The seventh one.
Okay. So this is something that you may need to do. If we want to operate dy and we're going to have to figure out what x is, you may need to rewrite things in terms of x. X equals. Okay. So we figured out what x is. X is just e to the y. So it's the integral of pi e to the y squared dy. And what else? What else do we need in this problem? The boundaries. So what are the boundaries?
1 and 2.
Yeah, boundaries are given in the problem. In this case, it's easy. So this should be from 1 to 2. There's your integral, and now you just got to do it. So first of all, e to the y squared. Do algebra, simplify that. What is that? E to the 2y. Now how do you do this integral? Nope. How do you do the integral of e to the 2y?
U substitution.
You have to do a u substitution. Because we know the integral of e to the y dy, but we don't know the integral of e to the 2y dy. So you have to do a u sub.
1 over 2.
So of course du is 2 dy, but we want to replace dy, so what's going to go in? Yeah. So e to the 2y becomes e to the u, and dy becomes half du, and I just pop the half out in front. So this integral, this one you guys know how to do. So you just get e to the u, and now we have to go back into y. So it's half pi e to the 2y, evaluated from 1 to 2. So just plug it in, you get that. Okay. So a quick comment. In doing this problem, when do we start doing calculus? Yeah. So where was that? That was right around here somewhere. That's where calculus started. Now, of course, you could say anytime we write down dy, we're doing calculus. And that's a fair point. However, the point I want to make is that everything up to that point is setting up the problem, just setting up the integral. So you need to think about, if I'm finding a volume, I'm going to be integrating the area. First of all, am I doing this dx or dy? Second of all, what's the area? And the sketch is going to generally help you out quite a lot doing that. So in this case, the shape is a circle, so the area is going to be pi r squared, and you need to figure out what's my radius, and that's where the graph can be very helpful. It's possible to do it without the graph once you get good at it, but in the beginning, I can't imagine how you would do this without a quick little sketch. Okay. Okay. So there's a side point that I want to make, which is a little fancy and advanced. And if you want to close your ears for the next 1 minute, that's okay. So once we got to this, let me see, this point right here, the integral of pi r squared dy, which is the integral of pi x squared dy. At this point, we essentially said, well, we have to solve for what x is, and we're going to do it that way. It turns out, if you understand differentials and change a variable really well, there's another way to do the problem using x as the variable. And everything that I'm going to show you, you don't need to think of it in terms of the picture. It's just a technique, a fancy technique of how to do an integral. So once we're at this point, integral of pi x squared dy, instead of rewriting x in terms of y, we're going to rewrite dy in terms of dx. This is a very slick trick. But this is something that we can figure out because y equals ln x. So what is dy?
Take the derivative of it.
Yeah. If y equals ln x, then dy equals 1 over x dx. And you're doing this integral. Now that's the first slick step. The second slick step is this integral is not complete, there's something missing. The boundaries of integration. Now, the boundaries of integration for y were 1 and 2. But when y is 1, x is not 1.
You plug it into the equation.
Yeah. When x is 1, you got to figure out what y is. Excuse me, when y is 1, you got to figure out what x is. And when y is 2, you got to figure out what x is. When y is 1, x is e, and when y is 2, x is e squared. And that we just know from the formula y equals ln x, or x equals e to the y. So when y is 1, x is e. When y is 2, x is e squared. So now you know that you're doing this integral. Yeah.
That's cool. I didn't realize we can do that to like dy.
And if you work it out naturally, integral of pi x dx is pi x squared over 2. Plug in and evaluate from e to e squared. And you get that, which is the same thing. So again, this is a bonus. This is a slick trick. This is not something that you need to know. But I thought, given the fact that we spent so much time when we talked about substitution, talking about changing from dy to dx or the other way around, I thought you'd be surprised and interested to see an application of that where it didn't seem like it would come up at all. So this is a moral that I'm going to say a couple times. I'm going to show you some guiding principles for how to do these problems. But to do each problem, there's usually more than one way to do it. So if you find your favorite way and always try to use that way, that's okay. All right. Now, if a region is rotated around the y-axis, one method of setting up the integral to find the volume is using disks and dy. And that's the couple problems that we just worked on. That's what we did. There is an alternative. And that's what I want to show you right now. Okay. Shells. Okay. So here is an enclosed region. And we're going to rotate this region around the y-axis. Now, typically, you'd say, we're going to rotate it around the y-axis. Let me take a horizontal slice, which is dy. But like I said, right now I'm going to show you an alternative. So an alternative is to take a slice that is dx. So a vertical slice, that's dx. Well, if you do that and you rotate it around the y-axis, what the heck do you get? You get a what?
Cylinder.
You get like the rim of a cylinder. Exactly. You get this. Now, what happens when you move all of them. Okay. So when you revolve all of them, you get a whole bunch of these. We call them shells. So it's like the shell, like the outside of a cylinder. Okay. So what the heck do we do? And in fact, just to make that more clear, let me make this a high number, and you can see. So now, okay. So now you can see we've really got these thin dx slices. And what happens when you revolve them? You can see that you get these thin shells. So how are we going to use this to make the volume? So when we had a disk, we said, okay, it's a circle, that's pi r squared. What's the volume of these things? And that's what we have to figure out.
Can we not say that it's a circumference, essentially it's a circumference of a cylinder?
Yes. That's
It's multiple circumferences of a cylinder. So it's like the area, the same way
Yes.
we solved at the beginning, the area.
yes, yes, yes. Okay. So when you have that, okay. So each one of these things looks like a shell like this, where I've made a cut in the shell, so I've opened the shell up a little bit. So the question is, what's the volume of this thing? Well, the width of it is dx. But the question is, what's the area of it? Exactly. To see what the area is, we're going to unroll it. So when you unroll it and you flatten it out, you will get a thin rectangular solid. Now the question is, what are the dimensions of this solid? Well, the thickness, as we know from the way we made our little rectangles before we revolve them around, that thin little thickness is dx. So right there we've got dx. Okay. What is the height?
The height difference in
Right.
in our leaf.
The height is just either the function, or if you've got two functions, the distance between the two functions. So that should make sense. Yeah. That should make sense from the picture. So the height of these things is just either the function, or in this case, the difference between the functions. Now the question is, what's the length?
2 pi r.
Yeah. Because what is the length determined by?
By the surface.
It's determined by the distance that you travel while you're revolving. So the distance, well, in what shape are you revolving? You're revolving in a circle. So when you travel around a circle, what's the distance? It's the circumference, which is 2 pi r. So there you go. So the height is the function, which is y, or y1 minus y2 in that case, and the distance is 2 pi r. And where does r come from?
The distance from the
R is the horizontal distance. Well, we've got a name and a letter for a horizontal distance on a graph, and what is that? It's x. So there's the volume of that slice. And naturally, what do we want to do with the volume of each slice? We want to add them all up. So you add them all up and find it exactly. It's an integral. Alternately, you could just think of the integrating area, and the area is length times width for that rectangle. So it's 2 pi x times y. Okay. So why am I showing you this extra method, which seems different and maybe a little confusing when we're already so good at disks? Oh, you know me so well. There will be questions you can't answer with disks. Okay. All right. So here I've given you a function and a little sketch of it. Y equals x squared minus 2x plus 3. And then also y equals 0, x equals 0, and x equals 3. So our region, roughly speaking, is that. Okay. So rotate around the x-axis, we know how to do that. I'm not even going to talk about that. But what about rotating around the y-axis? What would happen if you tried to use disks and set this up dy?
You could solve it using this,
Yeah.
we would have to divide it into two regions.
Well, over here your disk would be fine, but then what would happen? You get craziness over there. And it's not much fun over here either. Also, if you wanted to set this up dy, you would need to basically solve for y as your variable, so you need to solve for y from that function. Also not fun. So long story short, trying to do this dy with y as your variable is going to be a mess. But what about this new method? Can we set this up using dx? Can you take little dx slices? Well, yeah. That works out very easily. So that's no problem. But we have to recognize that we're revolving this around the y-axis. So if we're revolving it around the y-axis, what's going to be the area at each x value? What shapes are we going to wind up with? We're not going to wind up with disks. We're going to wind up with these things we're calling shells. And what's the area on a shell? 2 pi x y. Oops. Dx. Okay.
But now we have two variables.
Exactly. We want to integrate this dx. So having x in there is fine. Having y in there is not okay. But can we solve that problem?
We can rewrite it.
Yeah. And what's y?
Formula.
X squared minus 2x plus 3 dx. And finally, we have an easy integral. You need to distribute and all that, but you know this is this will give you something that you can do very easily. So I'm going to pull the 2 pi out in front as a constant, and you distribute, you get x cubed minus 2x squared plus 3x dx. And what's missing? The boundaries. So we need the boundaries for which variable?
For the x. No, for the y.
We are integrating with respect to what variable? Dx. So we need the boundaries for x. 0 to 3.
when you integrate,
Mm-hmm.
that's x cubed minus 2x squared over 2.
I didn't integrate yet. I distributed the x. I didn't. So yeah, so far all I've done is set up an algebra. Okay. So think about what it means to integrate with respect to x. We're saying at each x value, I'm going to get a certain thin slice. So for example, and we can see this with the picture. Let's do this. Okay. So what I'm saying is, at this x value, I get this slice, and it has an area. At this x value, I get this slice, and it gives me this area or this thin volume. At this x value, I get this thin slice, or this thin rectangle, which gives me this thin slice with its own thin volume. And I want to add all those up. So you're not adding up disks, you're not adding up the volume of thin disks, you're adding up the volume of thin shells. But again, each shell is determined by its x value. Okay. I know, it just got real, right? Okay. So finally, we can do this. So we can do this integral, no problem. But I know doing this integral is not the hard part of this problem. Someone. Okay. So let's see. Let's try to do some arithmetic. Yeah. Okay. All right. And then doing arithmetic, whatever that works out to be. Let's see. Yeah. I think that's right. Doing it in my head. Okay. 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 So let's do this problem. So let's work through this one together. So what do? Find the volume when the region bounded by y equals 2x squared minus x cubed and y equals 0 is rotated around the y-axis. So what's the first thing we should do? Draw a sketch. Okay. So what does this graph look like?
Upside down cube.
Okay.
A little bit.
It's a cubic, and it's going to be upside down, so it should look something like this. But we do need to figure out where it's positioned, because we need to know which part of the graph we're rotating. So how can we do that?
Positions at the origin.
Well, I would say,
Find x for y equals 0.
It's not shifted.
Yeah, exactly.
Vertically or horizontally.
So we know that one boundary is y equals 0. So why don't we figure out where the graph hits the boundary? And that's going to help. So 0 equals 2y squared, is 2x squared minus x cubed. So what do we do with that? Take out an x squared. 2 minus x. So what is x equal to?
0 or
You and two, I think.
0 equals, x equals 0 and 2. Now if this is a cubic, how come we only got 2 roots?
Because
Yeah.
0 is
0 is a double root. So that's very helpful because that tells us that at x equals 0, it just bounces off the axis. So we now know, in fact, exactly what this graph looks like. We know that it's going to bounce off the axis at x equals 0 and then cross at 2. Okay. So now we see exactly which region it is that we're rotating. It's this region. So yeah.
why can't we use this again? This.
Let's take a look. Can we use discs? So we have to compare. Do we want horizontal slices or vertical slices? So disc. So if it's rotating around the y-axis, which kind of slices would give us discs? Horizontal. So how would we do that? In theory, how would you do that?
one function minus the other one, but
Yeah.
here it's the same function. There's nothing minus the other.
Yeah. It's the same function. So you would need to, first of all, make
Second.
x a function of y, and then figure out where the function breaks so it becomes a top versus bottom relative to x as a function of y. So you need to figure out where this value is, where this value is, where that splitting point is. You need to do a lot of stuff in order to figure out what those things were.
Would the other function just be y equals 0?
No, because what's the length of each of these rectangles? It's one part of the one value on the function minus another value on the function. The way that we've drawn the rectangles horizontally. So perhaps this won't work. So what's the other alternative? Right. So draw vertical slices. So does drawing vertical slices work? Just on the graph? Yes. But if we're going to revolve it around the y-axis, what method does this give us? This gives us shells. Okay. So knowing that, the volume equals the integral of the area, and we've decided that, so making horizontal slices means what's your variable? Excuse me, making vertical, we chose to make vertical slices, and that means your variable is what? X. So everything is going to be with respect to x. Okay? Okay, so what is going to be the area?
The length and the width.
Okay, and what is that? 2 pi xy dx. Okay? And let's see. And I should, yeah. So a quick, actually, let's finish this problem, then I'll make a comment. Okay, so what else do we need to fix here? Okay, right. So the boundaries are 0 to 2. What else?
Take out 2 pi.
Take out 2 pi. We know we're going to want to do that. Okay, what else?
For value of 1.
Yep. X is x, and y is 2x squared minus x cubed dx. And now we've got something we know we can work it out. Blah, blah, blah. Yeah. So finally, what we see is we have options. So when you're given a problem, you have, let's see, you've got some choices you need to make. So there's one basic choice, and what's that basic choice? Yes, but I would say that that actually comes from answering a prior question. The prior question is, do you want to make vertical slices or horizontal slices? So in each problem, you're going to have a region. You're going to be revolving it around an axis. You have to figure out what makes the most sense. Do I want to take horizontal slices or vertical slices? And once you know that, then immediately that tells you you're going to do either discs or shells. So I'm going to give you a simple problem, and we're just going to see how these different methods may all be used at different times. Okay. So fx equals x squared, y equals 0, y equals 2. So let me see. Bounded by. There we go. So now I'm going to give you a couple different problems here. How do we find the volume when this is rotated around the x-axis and then rotated around the y-axis? So let's take a look. So rotate around the x-axis. How do we do that? What should we do? Sketch it. I think everyone believes that sketch is the right first thing to do. Okay. So rotate around the x-axis. Okay. So like this. Also y equals 0 and x equals 2. Okay? So if we're going to rotate around the x-axis, how do you want to set this up?
Using the horizontal slice.
Horizontal like this. So you make horizontal slices, and then you rotate around the x-axis. What is that going to give you? It's going to give you shells. Do we need to use shells here? Okay. So the other irritation about using shells here is how you're going to figure out what is the height of each shell. You have to take something minus something else. You could, truth is you could do it that way. So I actually shouldn't be so dismissive. You totally can do it that way. If you did it using shells, how would you set that up? The integral of 2 pi xy. We got to be careful here. So 2 pi times the wait, how do we say this? Times the height. Well, either way, x, y, or y, x, I guess doesn't matter. But d what? dy. Okay. So now you're going to have to replace x. So when you do that, how do you replace x? And for y, what are the boundaries of integration?
0 to 4.
Right. When x is 2, y is 4. So actually, you can use shells. And it's not terrible. How would this look if we set it up using disks? Right. So, or you can make vertical slices. And now what's the volume? Pi r squared dx. And what's r? It's just x squared. 0 to 2. Now notice this is crazy. We got two totally different looking integrals, but we've used our methods in solid fashion. It should be that they come out to the same thing. Let's check it.
I'm not sure why. I'm not sure why in dy we use 2 pi xy, because then we're kind of like rotating it.
So this one will be 4/5 pi times 4 to the 5 halves. And I'll just note that when it's 0, it actually does give you 0. So this gives you 4 to the 5 halves is 32. So you get 32 times 4, so you get 128 over 5 pi. Could it be the other one works out to be the same thing? Let's find out. Oh. Wait, did I do something wrong? Okay. I did some algebra wrong.
I think the first one, the y.
All right. So in similar fashion, we can take this region and rotate it around the y-axis. So when we rotate it around the y-axis, once again, there are two different ways to do this. So, let's see. Let me actually do this. Okay. So, now we're going to rotate it around the y-axis. So on one hand, you could make horizontal slices, and then what? And then the volume will be what? Visualize it. When you take horizontal slices and you rotate them around the y-axis, what shape will you get? You're going to get a disc with a hole in it. Because it's going to stay flat. So, disc with a hole means you have to do V1 minus V2. So what is the outer volume? So it's going to be pi r squared minus pi r squared. And d, what variable are we using? Yeah, horizontal slices are dy. And so what is the outside volume? What is the outside radius, excuse me? Look at the picture. Which equation gives you the outside volume? X equals 2. The outside one is x equals 2. So what's that? So based on that, what's the radius going to be? Radius will be 2. Now what's the inside one?
X squared.
Okay, well the function is y equals x squared, but what's the radius?
X squared minus 2.
The radius on the inside goes from here to here. And so what measures that distance? That distance is just x. Squared. But now, of course, if we're doing our integral dy, we can't have x in there. So what is x? X is the square root of y. And you can work this out, and it's an integral that you can do. Okay. Alternately, we can set it up the other way. You can say, here's my region. Instead of making horizontal slices, vertical slices. Now when you rotate this around the y-axis, what shape are you getting? Now you're getting shells because each one has a certain height and it's giving you like the rim of a cylinder, so it's a shell. So now, what's the volume? Integral of 2 pi r let's see. Yeah. Or 2 pi r times y dy. So, and what's the radius? So the radius is just x, but what's x? Oh, shoot, this should not be dy. Because they're vertical slices, which means we're working with respect to x. So what do we replace? What do we have to replace? Y. And what's y? Y was x squared. Now in this dx case, what are the boundaries of integration? X goes from where to where? From 0 to 2. And what about the other integral? The other integral is dy. What are the boundaries of integration for that? Not from 0. Y does not go from 0 to 2 on this picture. When x is 0, what's y? 0. When x is 2, what's y? 4. So notice that x values go from 0 to 2. Y values go from 0 to 4. So when you integrate dy, you're going from 0 to 4. Okay. As a last thing, let me clear up a mistake that I made in the first integral on this page. The proper way to do shells is to set up the integral with the area, and the area is really 2 pi r h. So to go back to this situation where the function is y squared, this is the region. R, with the rotation being around the x-axis, the radius is the y value. Now the height, if we're thinking about the shell, the height is actually this distance. So this is one of those cases where it's not just as simple as 2 pi xy. So in this case, the height is that distance, which is the distance between that point and that point. So it's actually, as measured along the x-axis, 2 minus the x value from the function. That gives us this. Now we've set up the integral with respect to y. So since we've taken these horizontal slices, so we can't have x in there, so we need to replace x. Well, x is just the square root of y. And that gives us this. And now this gives us, well, we have to insert the boundaries of integration, and since y values go from 0 to 4, those are the boundaries of integration. And we can multiply out that expression, and you get 2 pi times the integral from 0 to 4 of 2y minus y to the 3 halves. From here on out, it's a very simple integral. You get 2 pi times y squared minus 2/5 y to the 5 halves, evaluated on 0 to 4. You plug it in, and you work out the arithmetic, and you wind up with 32 over 5 pi, which is the same as doing it the other method. This was horizontal slices giving us shells, and this one was vertical slices, dx, excuse me, giving us disks. So this just goes to show that it is very useful to draw the picture, because these problems can be a little subtle, particularly if you're going fast and not paying attention. Okay.